This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion. Today we'll be delving into a research paper titled Solving Probabilistic Verification Problems of Neural Networks Using Branch and Bound. This paper proposes a novel algorithm for tackling probabilistic verification in neural networks, a crucial area for ensuring the reliability and safety of AI systems. Let's start with the core problem. What are probabilistic verification problems in the context of neural networks?
Probabilistic verification problems in neural networks involve rigorously analyzing the output distribution of a network given a probability distribution over its inputs. This is critical because real-world inputs are rarely deterministic. We need to understand how the network behaves across a range of possibilities, not just for specific, carefully chosen inputs. Examples include verifying fairness properties like demographic parity or quantifying the safety of a self-driving car's neural network controller.
So the challenge isn't just about whether the network produces the correct output in a single instance, but about the probability of correct or incorrect outputs across a range of inputs. What makes this problem particularly difficult?
The inherent complexity of neural networks contributes significantly. Their nonlinear nature and the vast number of possible input combinations make exhaustive analysis computationally intractable. Furthermore, the probabilistic nature of the inputs adds another layer of complexity, requiring us to deal with probability distributions rather than individual data points.
The paper introduces a new algorithm, probabilistic verification, PV. How does PV differ from existing approaches? What's its core methodology?
PV leverages a branch and bound framework, a powerful technique for exploring a search space efficiently. Unlike some existing methods that rely on expensive SMT solving or unsound approximations, PV uses computationally inexpensive input splitting and state-of-the-art bound propagation techniques like Crown. This allows for significantly faster verification times. It iteratively refines lower and upper bounds on probabilities, ultimately proving or disproving the probabilistic statement.
The efficiency gains are substantial, as the paper claims. Can you elaborate on the specific improvements over existing methods like fair square and SPACES-CANNER?
The paper reports significant speedups compared to fair square and SPACES-CANNER. PV solves benchmark instances that fair square couldn't solve within 15 minutes in under a minute. For the ACASU case study, PD achieved a mean runtime of 22 seconds compared to 33 minutes for SPACES-CANNER. These improvements stem from PV's efficient use of bound propagation and parallel processing.
This paper also compares PV to specialized algorithms for restricted subsets of probabilistic verification, such as #DNN verification. How does it fare in those comparisons?
Even against specialized algorithms for #DNN verification, a subset of probabilistic verification with uniformly distributed inputs, PV performs favorably. It outperforms Prove SLR, APROVE, and PREIMG APPROX in many cases, providing tighter sound bounds with greater certainty than the probably sound or approximate results of the other methods. This is particularly important in high-risk applications where absolute certainty is paramount.
The paper introduces a new benchmark, mini ACS income, to push the limits of PV. What makes this benchmark particularly challenging?
Many ACS income is based on the ACS income dataset, offering more complex, higher dimensional input distributions than previous benchmarks. It involves verifying demographic parity in neural networks trained on real-world U.S. Census data, making it a more realistic and challenging test of probabilistic verification algorithms. TV successfully solves several instances of mini ACS income, demonstrating its scalability and robustness.
The theoretical analysis of PV is also a key contribution. What properties of the algorithm are proven and under what conditions?
The paper proves that PV is sound, meaning it only produces valid proofs and counterexamples. Furthermore, under mildly restrictive conditions, primarily that the probabilistic statement isn't trivially true or false, it's also proven complete, meaning it will always find a proof or counterexample within a finite amount of time when using suitable heuristics.
What are the key limitations of PV, and what are potential avenues for future research?
One limitation is the requirement for the input space to be a hyperrectangle and the input distributions to allow efficient computation of hyperrectangle probabilities. While the paper discusses techniques to mitigate these limitations, extending PV to handle more general input spaces and distributions remains an open area for future work. Further research could also focus on improving the heuristics used for branch selection and splitting to further enhance efficiency. Exploring different bound propagation techniques beyond Crown could also yield improvements.
The paper emphasizes the importance of sound verification in high-stakes applications. Can you elaborate on why sound guarantees are preferable to approximate or probabilistic guarantees in such contexts?
In high-risk applications like medical diagnosis or autonomous driving, the consequences of an incorrect prediction can be severe. Sound verification provides absolute certainty about the results, whereas approximate or probabilistic methods only offer guarantees with a certain probability. This difference in certainty is crucial when dealing with potentially life-threatening situations. The cost of a false positive or negative in these contexts far outweighs the computational cost of achieving sound verification.
The paper mentions the related problem of verifying Bayesian neural networks, BNNs. How does PV's approach differ, and what are the trade-offs?
BNN verification deals with significantly higher dimensional probability distributions due to the probabilistic nature of the network parameters themselves. PV focuses on deterministic neural networks with probabilistic inputs, allowing for a more scalable and complete verification algorithm. The trade-off is that PV doesn't directly address the complexities introduced by the uncertainty in the network weights.
The paper highlights the importance of carefully designing the input distribution for probabilistic verification. What are the potential pitfalls of using a poorly designed input distribution?
A poorly designed input distribution can lead to misleading or even completely incorrect verification results. For example, an unfair classifier might be certified as fair if the input distribution doesn't adequately represent the real-world demographics. Therefore, the choice of input distribution is crucial and requires careful consideration and, ideally, validation by independent experts.
What are the broader implications of this research for the field of AI safety and reliability?
This research contributes significantly to the development of robust and reliable AI systems. By providing efficient and sound methods for probabilistic verification, it enables developers and auditors to gain greater confidence in the behavior of neural networks in real-world scenarios. This is crucial for building trust in AI and ensuring its safe and responsible deployment across various applications.
Finally, what are the key takeaways for our expert audience regarding the practical application of this research?
For practitioners, the key takeaway is the availability of a significantly faster and more general-purpose algorithm for probabilistic verification. PV efficiency allows for the verification of larger and more complex neural networks, making it a valuable tool for ensuring the reliability and safety of AI systems in various high-stakes applications. The paper's open-source code and the new benchmark dataset provide valuable resources for further research and development in this critical area. However, careful consideration of the input distribution remains crucial for obtaining meaningful results.
Thank you for this insightful discussion.